Hello again. Today we'll be talking about differentials, how to find them and what they're used for. Okay, so a differential, dy, is defined to be, well, let me start off. If you have a function y equals f of x, the differential dy is the derivative of your function times dx. This dy and this dx, they're both called differentials. A differential is an approximation to a change in the variable. Okay, we probably used this before. Delta x refers to a change in the variable x, and that's defined to be like x final minus x initial. So like change in y would be, y final minus y initial, or f of x final minus f of x initial, because y is f of x. Okay, so these are just changes in a variable. A differential is close to that. In fact, we're just going to define dx, which is the change in the independent variable. X is your independent variable. Dx is just going to be defined to be exactly equal to delta x. And then that brings us to the question, well, dx is exactly delta x. Is dy exactly delta y? The answer is no. It's going to be close to delta y, which is why we're going to be able to use differentials to approximate things. So let me show you with a graph. Okay, so let's say we have a graph of some function y equals f of x, and let's say that we're going from this point, this value of x, to this value of x. Okay, that would be my x initial and my x final, and the distance between them is the delta x. Okay, you can say that this is your y coordinate at x initial and your y coordinate at x final, and therefore this distance from here to here would be change in y. Okay, now dx is going to be defined to be exactly the same as delta x, and now let's try to find on this graph, what is dy. Okay, so we had defined dy to be the derivative of f of x times dx. Okay, imagine a tangent line at this x initial. That would be going like that. Okay, then if you make a triangle on that tangent line like this, this is dx, and this right here is dy. dy is basically the change in the y coordinate if you are riding on the tangent line. Okay, and notice that dy is almost exactly change in y, because the tangent line is very close to the function. Now, at least that's going to be true whenever dx or delta x is small enough. Then your tangent line is a good approximation to the curve. As you get further along, like maybe over here, this tangent line and the curve could be way far apart, and therefore dy would not be anywhere close to change in y. Okay, now last time we had been talking about linearization of functions and using a linearization to approximate a function. Differentials are really practically the same thing once again, because we're using a tangent line. We're calculating this thing called dy, and it's going to give us a good approximation to change in y. So if this is something that we can use to approximate things, when do we use linear approximation and when do we use differentials? Okay, so linearization is used when you're trying to approximate the value of a function at a single point. Differentials are going to be used whenever you want to approximate the change in the function between 2 points. So differentials are more useful for changes. whereas linearization or linear approximation is more useful when you're trying to approximate at a single point. Okay, let's do an example. Okay, let's say that we have a snowball, which is going to be a perfect sphere. And let's say the radius of the sphere starts off at 3 inches. Okay, but the snowball is accumulating snow and the radius is increasing over time. So that we can say that the change in the radius, so change in R or dr, is going to be 0.3 inches. So it's going from 3 inches to 3.3 inches is another way of saying it, okay? By how much would the volume be changing approximately? So using differentials, we want to approximate the change in volume. So the volume equation for a sphere is 4/3 pi r cubed. Then we use differentials. So dv is the derivative of the right side, so bring down the 3, reduce the power by 1, and then times dr. So notice that, it wasn't y and x, it was v and r, but it's, really the same thing. Anyway, now that we have this, we can simply plug in that r is 3 and that dr is 0.3, and we get the approximate change in volume. So it's going to be 4 times pi times 3 squared times 0.3. Let's see, so that's 9 times 0.3 would be 2.7, and then 2.7 times 4 is 10.8. 10.8 pi is the approximate change in volume. Now, let's find the actual change in volume to see if we are actually close or not. Okay, so I'm just going to keep that there and calculate change in volume just by considering the volume final, the volume when the radius is 3.3, and subtracting the volume at 3, and that'll be our change in volume. Okay, so our change in volume is going to be our volume when the radius is 3.3, which would be that equation, minus the volume when the radius is 3. Okay, I'm going to use a calculator. It's a little bit hard to do 3.3 cubed in my head. Okay, so 3.3 cubed times 4 divided by 3 is 47.916, and then times a pi. 3 cubed is 27. 27 divided by 3 is 9. 9 times 4 is 36. So it's 47.916 pi minus 36 pi, which is, and that's not even approximate, that's exact. Subtract those and we get 11.916 pi. I kept the pi in there so that it's easier to compare them since there's a pi in this equation. So 10.8 pi, 11.916 pi. Pretty close. Now it's not as close as maybe you'd like. This is about a 10% error. But the reason for the big error was because this was growing from 3 to 3.3, which is a pretty big growth. If I had made this smaller, these would have been a lot closer. Okay? Now, a similar problem, instead of having a snowball that's growing in size, I could have presented the problem as, let's say you have a sphere, and the sphere has a radius of 3 inches, and you coat it with a coat of paint. And the coat of paint is 0.3 inches thick. And I wanted to find what volume of paint do I need. The volume of the paint would be the difference between the sphere with the paint on it minus the sphere with, without the paint. That would be the volume of the shell. and you would do the exact same procedure. So this would be your approximate amount of paint that you need to buy. Okay, so I think that's going to be it for today. Just one quick example of using differentials. Like I said, they're going to be used more in problems where you're trying to find the change in a function rather than finding a function at a single point. Anyway, that's going to be it for today. Hope to see you all later, and have a good day.